And today we're having Istvan Prause, and he's going to talk about integrability of limit shapes. And as far as I understand, it's going to be the continuation of the last week's talk. Thank you for coming.
Yes, thank you very much. Thank you for the invitation. Yes, so I'm going to talk about two joint works with Rick Kenyon from Yale, and he in fact gave a talk last week on the 5-vertex model, describing their work with Jan de Geer and Sam Watson. And this is a continuation in the sense that really that was the starting point of our collaboration. So they used the surface tension for this 5-vertex model, but you may remember that it's kind of a complicated expression from last week. And so we try to understand if there is some special property and what is the difference compared to the timer model, and partly also to develop a framework which would apply in general for non-determinantal settings like the 6-vertex model and so on. But actually there will be also some simplification even in the diagram model or determinantal models, as we will see. So at some point I will reference some results from last week, but the talk is basically self-contained talk. So I will start from the beginning. So and describe what I mean by limit shape. So for this, a good starting point is a limit shape of 2-dimensional Young diagrams. Namely, we will take some large integer now, and then we partition it where we don't care about the order of this partition. So it can be represented as a monotone sum of smaller integers. And then you can picture it as a 2-dimensional Young diagram. So we have here 5, 4, 4 in the rows 2 and 1, 1. And now what happens is that we take a large integer number n, and then we we can partition it in many ways. So, but in any case, finitely many ways. So we take uniformly random such partition, and let's draw the associated Young diagram, but at the same time rescale the picture so that it has a fixed macroscopic scale. And then what happens is that there is a deterministic limit curve here, so that almost overwhelmingly large majority of the partitions lie close to a fixed curve, which is parameterized by this equation. The constancy here depends on how exactly we did the rescaling. And of course, there are some outliers which lie from this, some partitions which lie far from this curve, but those are extremely rare events. So in a random configuration, there is no chance of seeing those. So there's a strong concentration of measured phenomenon in this macroscopic scale, and this is exactly the kind of phenomenon what we are going to talk about, limit shape formation from a microscopic size to macroscopic scale. But instead of 2 dimensions, we will look at 3-dimensional random surfaces. So in this case, a nice illustrative example would be, well, instead of 2 dimensions, 3-dimensional Young diagram limit shape. And somehow this is easier now to imagine from the complementary point of view. So imagine that we have an infinite corner here consisting of small cubes. And then it's like a crystal corner. We start melting this crystal. So we remove a certain number of small cubes, but in such a way that the formed surface stays monotone in 2 directions. So for instance, if you are only allowed to remove one single cube, we are forced to remove from the corner. So again, what we're going to do is remove more and more cubes, and at the same time rescale the picture such a way that the fixed missing volume is something fixed. And again, there is a limit shape, a limit surface in this case, which has the property actually that there is a certain facets surviving even in the limit. So in these 3 facets, here is the limit surface, and then there is a curved part in the middle, a smooth rounded part. Now there is some connection of this picture to two-dimensional tiling. Namely, if instead of cubes you project this to the plane as it is actually in the screen, then you have a lozenges, three type of rhombi, and you can as well view it also as a tiling picture. But there is also another kind of projection coming from C2. So there is a connection to algebraic geometry, namely that this region here, this curved region, is actually an amoeba of an algebraic curve. So what amoeba means in this, so we have some polynomial relation between two complex numbers. So ZW in C2, and then, well, it's some surface or some algebraic curve in C2. It's kind of difficult to visualize, so often useful to do this, take the modulus of Z and do the log-log, and also for W, and do the log-log projection. And this way we have something in R2, and this is actually this is the so-called amoeba of this curve P. And in this case, so we had a three-dimensional limit or crystal surface projected to 2 dimensions. Is exactly this curved part is exactly the same as a projection of this certain algebraic curve from C2 via this amoeba projection, and the curve itself is actually the simplest curve what you can imagine is a complex line. This is in fact not a coincidence, it holds true in more generally for in case of the Domino model. So this formation of facets, what we have seen here, one of the starting points is the Arctic Circle phenomenon. So we have this so-called Aztec diamond shape, but we again tile now with the dominoes in a uniformly random way. So there can be horizontal or vertical dominoes. Here, in fact, there are 4 different types of dominoes because you can orient them as well. And this is a uniformly random picture. In the limit, you once observes a perfectly round circle inscribed to this square, and then you have these frozen parts in the corners. And similarly for lozenges, if you tile the regular hexagon, again you have frozen facets and the inscribed circle. Now you can study this kind of problems in many different ways. There are some deterministic point processes behind, and so on. But what we're gonna ask or address here, that there are some harmonic functions behind these pictures. What are those harmonic functions? And for this, the kind of the approach what we take is a variational approach, which has the advantage that it unifies many things. So it kind of works for general boundary conditions. So for instance, if you remove here from the hexagon some part, you modify the boundary, you get a different frozen boundary, in this case a cardioid. But also works for a variety of models. So I will mention some timer models, namely Domino and lozenge tiling models, and some random Young tableau. This is a picture simulation for a random Young tableau in the middle, and then also something about the 5-vertex model. This picture is actually a 6-vertex model simulation, so this is a more mysterious what's going on here. But for 5-vertex model now, we have a fairly good understanding. Okay, so how to view this, or what is this variational approach? The first thing is to introduce a height function, which in the case of this lozenge tiling model is a very geometric, is exactly the kind of these cubes that I talked about of the melting crystal corner. So instead of a tiling picture, you can view this as a 3-dimensional step surface if you imagine this as cubes. Technically, it will be often more convenient to normalize the gradients to the 3 discrete gradients. So in that case, some affine transformation is involved. In any case, a key point for this talk is to really view these limit shapes of surfaces in 3 dimensions. So I show here a simulation by Alexei Borodin, where this tiling picture is now rotated in 3 dimensions. I think Rick also showed this last week or something like this. One thing that we see is that the boundary conditions, they are very non-planar. And this is needed for this formation of facets. Okay, now, what is the limit shape theorem and the associated variational problem? So just like in the case of the 2D Young diagrams, here it says that as we have, again, we will send the mesh size to 0, and the macroscopic scale is something fixed. Then for a given boundary conditions, the associated random surface lies close or concentrates around a deterministic surface, which we call the limit shape. So this is the limit surface in R3. Moreover, so in this limit, the randomness disappears and you get something deterministic. And moreover, this limit shape is a minimizer of a variational problem. So what is the variational problem? We have some R region omega in this box plate partition example. When we get a hexagon, this omega would be the regular hexagon. Above that lies we have the height function h. So in the limit, in the limit, there will be some Lipschitz function with a gradient constraint. So the discrete gradients were taking in 3 corners in a certain triangle. So in the limit, it will lie in a convex combination of this triangle. It's denoted here by n. We also have some Dirichlet boundary conditions. So we want to span a given this non-flat boundary conditions. And what we want to minimize is a certain surface tension integral. So sigma of gradient h above this region among such functions. Now, but the surface tension only depends on the gradient, so it's a kind of a gradient variational problem. You can notice, well, it's kind of a minimal surface problem. So if you would have a wireframe minimizing the ossium, so in that case, we would want to minimize the area, spanned area. In that case, this would be the surface tension. In our case, the surface tension is something non-isotropic and also more singular. So this is the actual picture for the lozenge tiling model. Surface tension looks like this. It's constrained in this unit triangle, but it's singular on the boundary. So here the gradient escapes to infinity on these edges, and also it's the eigenvalues of the Hessian degenerates to 0 and infinity. So it becomes quite, but inside it's nice analytic and cyclic convex surface tension, but on the boundary it's quite singular. All right, so, but what is this surface tension? Well, whenever you have this kind of some surface tension, the groove shape is a volume constraint minimizer to the surface tension. So which is the Legendre, if you now consider the Legendre rule of the surface tension, it will be a volume constraint minimizer. So we can say that the surface tension is now the other way around, that the surface tension is the Legendre dual of the groove shape. Of course, this is now sounds a little bit circular argument, but the point is that the groove shape itself arises as a limit shape from the problem. So if you can solve that this is kind of the ultimate limit shape of the model. If you can solve this limit shape problem, then you have the surface tension, and then that via the variational principle governs all other surface tensions. Namely, in fact, for the lozenge tiling model, the groove shape is exactly 3D Young diagram limit shape. So in that sense, it is the fundamental solution. And also because we see here that many of the features already appear for the wolf shape. And in fact, because the wolf shape has facets, it means that the Lejeune dual, the surface tension is singular on the corners, and that's why other minimizers also have facets. And then what kind of transition you have on the boundary. Also, this connection with the algebraic geometry is responsible that in more generality, the frozen boundaries tend to be algebraic, at least for the dimer model. Now, an important result, especially for our purposes, will be the theorem of Kanyanov-Kunkov-Sheffield at the Hess. So this surface tension is something complicated, singular, but it has a nice property that its Hessian determinant is constant. Well, in the usual normalizations, it's constant pi squared, and this is true for the dimer model or more generally for free fermionic models. Now, once we know what the surface tension is, one can actually consider this differential problem and discuss the limit shapes in the model. So here I describe only results related to this differential approach. So the first result is the Kanyanov-Kunkov paper, which they reduce the Euler-Lagrange equation to complex Burger's equation, and in fact match for a given this kind of polygonal boundary condition, match a limit shape for the Lozenj model to the given boundary conditions, and find that the frozen boundaries are special kind of algebraic cloud curves. So here how this complex Burger's equation arises is that they rewrite the Euler-Lagrange Euler-Lagrange equation in terms of this CW, this so-called spectral curve variables. Now we studied with Karyastolov, Eric Dusse, and Chao Zhong the same kind of problem for a general dimer model, but a little bit from the opposite point of view, namely that there is a unique minimizer, so we know the minimizer exists, and then we can start to prove more and more things about the minimizers. And we also introduced this complex variable in a little bit equivalent but equivalent way in terms of partial Lejeune transform. In that case, the Euler-Lagrange equation becomes such an equation that in this d bar of this complex function z becomes something holomorphic of the same function z times the d of z. This exact function depends on the model or on the surface tension. So in terms of this is d bar over d is the Beltrami coefficient. So if you rewrite in terms of that, it says that mu of z is something holomorphic of z. Well, this in principle depends on the dimer model, but now one can take this Beltrami equation once more, and then because this was holomorphic, we find that the mu of mu, so iterated now twice, is the same as mu. So from this equation, it disappears the sigma, the model dependence. And on the other hand, this equation is sufficient to recognize the frozen boundary because the equation exactly degenerates on the frozen boundary. So in this sense, actually the frozen boundaries are in a sense among the dimer model are universal, that everything but can appear already appears for the Lozenj model because this is the equivalent for the Lozenges. But for both of these papers, the key property what was used is this free fermionic property that the Hessian determinant is pi squared. So this is quite explicit in our paper. In the Kanyanov-Kunkov paper, they use the Harmonic curve property, which is in a way is equivalent to this one. So now the focus of this talk is what to do beyond dimers, so non-pre-fermionic models. In that case, there is no complex Burger's equation. This property will fail. Also, the curves are not going to be algebraic in general. But okay, because before going there, I will let me discuss a little bit this pre-fermionic property, because it's a bit of a mystery. So why is this, or what? Well, I said one in a mathematics language. This is a statement that the spectral curve of the model is a Harmonic curve. Physicists have their own understanding of this, namely, in the physics literature, there appears this in different names, this parameter, Luttinger parameter, or stiffness constant, which is the pi divided by the square root of the Hessian determinant of the surface tension. And so for a free fermionic models, this is a constant 1. And what are the consequences of this property? That there is a universal growth of the height variance in the liquid region. This constant is universal. Then that there is there is this non-trivial complex structure for the fluctuations that one expects, and in many cases proved, is the GFF fluctuations in a non-trivial complex structure in curve, but nevertheless it's a homogeneous, it's a conformally invariant GFF. This is then also responsible for that we have algebraic boundaries, and what I mentioned, that it's kind of macroscopic universality. So now let's see what I still wanted to recap the logic here. So we have this kind of let's say this like the Aztec diamond limit shape problem. So with certain boundary conditions, we can. I told you that this is can be studied in terms of variational principles. So given boundary condition, we want to minimize a certain surface tension integral, but I have to tell what is the surface tension. Surface tension is the Legendre of the Wolf shape, but now I have to tell what is the Wolf shape. Well, the Wolf shape is the free energy in the magnetic field, which this is the Skenyanov-Sheffield paper, which can be then eventually calculated using the integrability of the model. So once we have this, we can actually write down the PDE for this minimization problem. And now the question is that we started with this integrable model. How does this translate on the PDE side? Or in other words, okay, so we have some surface tension. Maybe we can write down explicitly. We can then, this is the Euler-Lagrange equation, but how would you go about solving it? So this, I took this slide job from Tadeusz Iwaniec. He usually uses this for integration by parts. Now we'll adapt to our situation. So for instance, for the Lozenc model, you can write down everything explicitly, but it's a very nasty equation. You don't, it's not really clear how you would solve it in a concrete way, or especially match to given boundary conditions and so on. But recall that even to derive this sigma, it was coming from this spectral curve. So at the complex Burger's, how the complex Burger's equation arises is rewriting this equation in terms of those variables. So that this is well, what we will see also for the 5 vertex case. And kind of the slogan here is to complexify, to simplify things. So we introduce a complex variable in terms of which everything will become much simpler. Now it's a bit hidden complex variable, but not that hidden, because if you think about fluctuations, there should be some non-trivial complex structure according to the physics predictions. Or as I said, in the integrability of the model, there also appears some complex variable. But what we are going to do is actually an abstract approach and introduce it as an isothermal coordinate. So let's do this. So we have some model. There is a loop shape associated to this. It's well, we don't know a priori what it is, but well, it's some. Let's assume it's some nice convex, faceted, but there is some convex part to it, and so there is a Riemannian metric associated to that groove shape, or equivalently to the surface, to the unknown surface tangent, namely this Hessian matrix of sigma. It's a 2 by 2 positive definite matrix. It defines a Riemannian metric in this S. So I use ST coordinates for the surface tangent variables, the slope variables, which lie in some gradient constraint region. And then this we're gonna encode with a complex number Z, which can often it's not uniformized to the upper half plane, or maybe to the unidiscrete, depending on the convenience. So, and we introduce this as the isothermal coordinate associated to this Riemannian metric. Now, this was done on the loop shape level, but then at the same time, we can do this also for any limit shape on the liquid part. Namely, so I use now the small xy coordinates for the liquid region. It means that there is a well-defined gradient to the height or to the limit surface there, which is given by some certain slope, which then already be associated to complex numbers. So we have this mapping, complex solid mapping from the liquid region to the complex numbers. And this is kind of turns out to be the right conformal coordinate of the model. So now the slogan is to write everything in terms of this complex Z. For maybe I will need for future reference. So the partial derivative of sigma I denote by capital X and capital Y. So this small x and small y live in the liquid region. This capital X and capital Y live on the kind of the amoeba associated to the groove shape. So the sigma and sigma t. Now, okay, what is our theorem? Or well, first we need some definition or notation. So we have seen that this Hessian determinant, even more precisely the square root of the Hessian determinant, was important. So let's take this thing. So this is now lives in the ST variables, but the ST coordinates depend themselves on this complex variable Z. So we can view this square root of the Hessian determinant also as a function of Z. Let's call this kappa of Z. And then we say that the function is kappa harmonic if kappa times the divergence of kappa times gradient u is 0. So here kappa is a conductivity term, so it's a non-inhomogeneous Laplace equation. Now the theorem is that we have three functions, S and T, and also this third function, which is the height function minus the inner product of the slope, ST, with the liquid region coordinates XY. So that these three functions are all, we all view them as functions of this complex Z. They are all kappa harmonic in this variable in the liquid region. And the reason for this is that because of this isothermal coordinate, but it says that the gradient of T times kappa, the Hodge star of that will be the, for instance, the gradient of X. Oops. But X I introduced in the previous slide. So it means that this is a curve-free vector field. So we have here this Hodge star. So this is actually a divergence-free vector field. So T is a kappa harmonic function according to this definition. Similarly for S, and more importantly, the third function is Kappa harmonic because that's exactly the Euler-Lagrange equation in terms of the z variable, as it turns out. The only caveat here is that this, because the inverse from the wave shape to the liquid region is not single valued, so this is a multi-valued function in the third function. But now let's see what it means geometrically, this theorem. So recall that St was the slope term, so it's a gradient of the height function above certain. So we have a point xy in the plane. Above that, we have the limit shape at a certain height. There is a tangent plane to this limit surface, and St gives the slope of this plane. But then we also have to find this tangent plane, we also have to tell that at what height this tangent plane is, and that this third function exactly describes where this hits the vertical, the third axis. So it means that we have a family of planes parameterized by these three coefficients. There are three coefficients, which they move in a Kappa harmonic fashion in terms of the z. So and they carve out a certain surface, and that's this envelope is the limit surface. Now, since in the diameter model this square root of the Hessian, as I said, was constant, we can as well normalize it to be 1. Then we just have the usual Laplacian. So then we have harmonic functions. So as a corollary, we obtain that the diameter model limit shapes are envelopes of harmonically moving planes in R3. There is a kind of duality here to limit minimal surfaces. So minimal surfaces also can be parameterized by harmonic functions in terms of the isothermal coordinate. And that's because the associated, so there is this Beltrami coefficient behind when introducing the isothermal coordinate is anti-holomorphic. In our case, this will be holomorphic, and what it means that this Legendre instead this Legendre dual coordinates will be harmonic. So this hx, hy, st, and this third function. But also then this leads to a way to match limit shapes to a given boundary condition. So for instance, in the hexagon case, we can expect or try to construct such a limit shape that has 6 facets in the 6 corners. So we know in each corner we know the slope of the facet from the boundary conditions, but and also know at what height these facets are. So it means that we know all the boundary values of all 3 involved functions. So let's we can construct the harmonic extension, and we obtain this family of planes, and then find the envelope, and then this is the constructed limit shape. So this can be called the tangent plane method, and then there's a resemblance to the usual tangent method of Colombo-Sportiello, and also also of Agarwal, for the which is more rooted directly at the probabilistic model, which also constructs the Arctic curve as a family of as an envelope of family of lines in that case. So the advantage there is that it works also even for instance, in certain boundary conditions for the 6 vertex model, when we don't exactly know what the surface tension is. But on the other hand, this one gives the full limit surface. So from this point of view, we can revisit also the domino tilings of the Aztec diamond. Again, we are looking for an envelope of planes of this ST, and the third coordinate, I call it C. So this is the equation of finding, we take the z derivatives for all coefficients of finding the envelope. So in that case, it's convenient to normalize, to have this Z variable in the unit disk, in which case the ST mapping as a joint map becomes a harmonic mapping to this Newton polygon, collapsing this quarter arcs to the appropriate corners. So more explicitly, S is a certain combination of these harmonic measures, and T is another combination of other harmonic measures. But like from here, from the picture, we see that because we know the facets, we also know the boundary values of C. So it jump here. It's on the blue part, for instance, it's something here, the -1. Then on the red part, it jumps up, and so on. So this will be then this type of combination of harmonic measures. And then we can solve these linear equations and find the limit shape parameterized by this Z variable. Now this works also for other kind of models. So for instance, this is an example for Young tableau. We can look at a square shape here and as a Young diagram, and then fill the cells in a monotonic manner in both directions, so from 1 to, well, in this case, to 100, to consider random Young tableau. And well, there is also discrete surface associated with this, namely the height is as the number it gives. So we put as many cubes in each squares as the number says. It will have this type of level lines, this surface, and this was actually this particular example was worked out by Pittel and Romick. But from more general boundary condition, so in general, Wang-Rusan deduced also variational principle for this Young tableau problem. Again, because this is a determinant problem, this Hessian determinant is constant, so this kappa is constant, which means that we have nice harmonic coordinates for the surface tension, and also then limit surfaces are harmonic envelopes of planes. So for instance, in the square construction, this would be the boundary condition. In this case, we have 4 facets, and we do the harmonic extension of the boundary facets and find the limit surface. And here you can see the actual discrete surface. So from a certain projection, you see this also this Arctic ellipse inscribed to the rectangle. Now, okay, so we have seen that there is this kind of zoo of limit shapes, and okay, the determinant for determinantal models, everything is nice because the kappa is constant, so we have harmonic dependence. We can use this harmonic envelope construction. Question is what happens for non-determinantal models, like what is kappa, for instance, and how can we study the limit shapes. So before going to the 5-vertex model, let me just make a definition. So we have seen that kappa, in general, we have this kappa harmonic dependence. So one way to study kappa harmonic functions is to reduce, instead of looking directly at them, reduce to the Schrödinger equation. So introduce a potential Q, which will be the Laplacian of square root of kappa divided by square root of kappa. And instead of asking what U satisfies, asking what square root of kappa times U satisfies. So satisfied that minus Laplacian plus this potential is equal to 0. Now, if kappa, like in the free fermionic models, this kappa is constant, it means that this potential is 0. So in that case, Q is equal to 0. But in principle, this Q can be 0 also if kappa is not necessarily constant. If just square root of kappa is harmonic, then this is already 0. So let's make this as a definition and say that the surface tension is has a trivial potential if this Q is equal to 0. So in terms of, because kappa was the square root of the Hessian determinant, it means that and we took one more square root here. It means that altogether we have to take the fourth root of the Hessian determinant. If this is a harmonic, so Laplacian is 0, if this is a harmonic function of this intrinsic coordinate z, then it is nice, because in that case, Q is equal to 0. So this thing will be also harmonic, and square root of kappa is also harmonic. So our original interest, this kappa harmonic function, will be a ratio of this function, which is harmonic, divided by some other harmonic function, which is this fixed fourth root. Now, now I come to the 5-vertex model, which Rico already discussed last time. So I just go here briefly that one can view it as a monotone non-intersecting lattice path, probability measure on monotone non-intersecting lattice path. So like this, we always go north or west at each step. And what will be the probability of a given configuration? So at each vertex, we have 5 possibilities, because we require that the paths are non-intersecting. So there might be that there is no path going through, or we go vertically, horizontally, or make a turn. And in case we make a turn, we assign a non-trivial weight r. In other cases, just 1. This type of Boltzmann weight. So for a given configuration, we have to count that how many turns we see in the picture, and multiply, well, add them up and take r to that power, and then the configuration will be proportional to that weight. So when r is non-zero, then this destroys the determinantal structure. So in the physics language, the fermions become, they interact, or in other words, we now penalize or favor having corners. One can also introduce here the height function. This lattice path will be the level lines for the height function, or also view this as a lozenge tiling, but with an interaction between the blue-green lozenges. So we again have to count at how many neighbors, blue-green neighbors appear, and count with this weight r. Now, well, okay, there is a, so far there I only used one parameter. I explained that there, in fact, altogether there are 3 parameters. And that we can view this as introducing a magnetic field. This is kind of important, but not relevant, for instance, for this question. So we can again ask that what is a random box plane partition, kind of for the box plane conditions, what is a random configuration with respect to this 5-vertex measure. So we have here a hexagon shape. This is kind of a staircase boundary here, and the boundary condition is such that we send in the path along this diagonal and make them come out on the opposite end, and no paths are entering or exiting on the other sides. And then this is a simulation of a random such configuration. We again see some facets in the corners. So here we only go horizontally, here vertically, and here there are no paths, and so on. And then there is an disordered region in between. But now this is not quite an, so if r would be equal to 1, this would be the perfect ellipse. This is now a deformed version of the ellipse, not exactly an ellipse. And even in this close to this region, there is some fuzzy thing going on. So this is from Rick explained last week, the results obtained with the Tegir and Sam Watson, that well, they have been able to carry out the beta ansatz solution to actually describe exactly the wolf shape and also the surface tension for this model. It's kind of involved formulas there, but the nice thing about it is that it does have a trivial potential. So namely, this is in terms of this intrinsic complex variable, the square root of the Hessian determinant. So this kappa is a square of a harmonic function. So a new feature here is that so in the usual dimer model, but these tentacles escape to infinity. Here there is a finite point where they meet, the blue-green parts. So in terms of the plane projection, we have this so-called conical point here. So what happens intuitively, that on the boundary the interaction is not felt, so that we have the kappa is everywhere on the boundary, is actually the same pi as for the free fermionic case, except at this special point where actually the blue-green meet, the interaction is very much fat, and the kappa is then on that part is actually equal to 0. And that will result to this affine or flat part of the surface tension. So, namely, if you know this boundary values, then this will be the harmonic. So then the square root of kappa should be harmonic. So this will be then the harmonic extension for these boundary values. And from this kind of knowledge, one can actually then reconstruct the wolf shape or the free energy, more precisely the one-parameter family. So we can arrange this complex. So it's better to arrange things symmetrically. So this complex, there will be actually two complex coordinates, z and w, one corresponding to tx mixed tx, so the slope t and magnetic field x variables, and the other one is to s and y, and they will, but nevertheless they define the same conformal structure, so they should be conformally related. And because we arrange things so that this conical point corresponds to the unit interval, we can normalize it there. It will be actually a Möbius relation which fixes this interval. So there is only one parameter freedom here, this r squared for this relation. Now, if we accept that kappa has these boundary values and that it has trivial potential, then as I said, this will be the harmonic extension. So we know what kappa is. Then, because kappa is a trivial potential, we know that T is kappa harmonic. We know that it's a ratio of a harmonic some harmonic function divided by this concrete harmonic function, the square root of kappa. But from the boundary values, for instance, we can put here that in this part T is equal to 0, here T is equal to 1. So it means that the numerator has to be the argument of Z. And then to find x, we have to find the kappa harmonic conjugate of T. So while solving this equation, it's also possible. Of course, now I'm kind of doing backwards what from the beta ansatz solution was found. But this, I'm just trying to emphasize that this trivial potential property is it then basically determines the surface tension. Then we can find also x, and then from this symmetric relations we phi also y, and s. So there is now a relation between x, y in this amoeba region to find what the slope st is. That gives the gradient of the free energy via this complex numbers dw. And then finally, integrating once more, one can find the free energy. Okay, but now let's go back and look at this box plane partition example. What's going on there? So this is the amoeba picture. It has these three facets, but there is also this conic extra face for this conical point. So again, we have now for the finding the limit shape, because it has trivial potential, we know that it's an envelope of planes for which the coefficients are ratios of harmonic functions. So in that case, we actually have again from the boundary conditions in the facets, we have full boundary information, and on the conical point is a bit so which would correspond to this part, it's a bit more tricky because here there is no facet in the limit shape. So, but nevertheless, it's a ratio of two harmonic functions, and in that part actually both, because both harmonic functions vanish. So in terms of the harmonic functions involved, we have full boundary information, and then the limit shape is an envelope of this kind of planes where all the coefficients are explicit ratios of linear combinations of harmonic measures in terms of this complex parameters. So in the r equal to 1 case, this would be without these ratios. It would be just simply linear combinations of harmonic measures. What Rick mentioned last week also is that there is this fuzzy part. So actually the statement is that because the surface tension in this small r case, when r is smaller than 1, is not strictly convex, there is no unique minimizer to this boundary condition. So what it means is that the random surface, but nevertheless the minimizers have this property that except this purple region, they all agree. So what it means that the random surface lies, so the limit shape is only formed except this purple part. So all the random surface lies close to this deterministic limit surface, and in this part, it may happen that if we resample, then there is a macroscopic change. There is a change of the limit surface even in this macroscopic scale. This is a bit mysterious. We don't know, and actually, but it seems that this actually does happen. Now there is, let's see now an example when this r is bigger than 1. So it's 2.5. In that case, this would be the Arctic curve associated to this limit shape. So here, we have, for instance, a zigzag facet. So if you want to have lots of corners, we have corners everywhere. Now, I told you that in the Domino model, the frozen boundaries tend to be algebraic for this kind of extremal boundary conditions. In this case, this is certainly not an algebraic curve because it's non-analytic at this tangency point. So there's a tangent, but the second derivative has a discontinuity. But in fact, this is the only reason that this is not an algebraic curve. So if you would continue this part is an algebraic curve, and if you would continue algebraically this curve, then to get to this second part, you have to apply a shear transformation and so on. And moreover, this underlying algebraic curve arises as a domino Arctic curve. This type of phenomenon has been also observed for other non-fermionic models, so this would be something interesting to understand better. This is the associated free energy or loop shape in this case. But now I'm kind of running out of time, so let me revisit this integrability of limit shapes. So this is what the diagram we had before. We have seen that introducing this intrinsic Euler-Lagrange equation and intrinsic coordinates, we get a nice integrability in terms of harmonic functions. And then on the other hand, this integrability of the model is so well in the Reimer model in terms of clustering matrix. In the 5-vertex case, it's using the beta ansatz. And then the right intrinsic coordinate is actually appears, we so introduced it in terms of, it's not a thermal coordinate, but it really appears already on this other side also of the model. So in the 5-vertex case, it's the endpoint in the contour integration or in the beta ansatz. Now, what we did with Rick going further with this 5-vertex model is that we introduced a staggered or inhomogeneous model. So where there's a periodicity with respect to some higher periods, M1 by 2 fundamental domain. So the vertex weights would depend on the location of this of the vertex in this fundamental domain, and these are the specific weights what one can consider. So we have to modify this empty vertex a little bit to make this work. And then there is also two cases: the small r case when all of these. So and also an important condition is that these numbers are not arbitrary, but they factor in terms of the horizontal and vertical component. And then all of them is either smaller than 1 or bigger than 1. So we have this kind of repulsive or attractive interaction. And in each, so by having a common conformal coordinate, this can be reduced to the simply periodic model. And then the result is that, in both cases we can derive the explicit surface tension, which has this kind of phase, this kind of shapes. And in the larger case, the surface tension is strictly convex. So in particular, there's a unique minimizer. There's a limit shape formation everywhere in the domain. In the smaller case, again, there is a region of non-uniqueness, where in our normalization, actually, the surface tension is constant 0, just like in the simply periodic case. But in both cases, it has a trivial potential, and there is a kind of duality in between the two sides. So it's this kappa, square root of kappa, is the argument of a complex number, or in this case, the complementary angle. And using then this fact that it has a trivial potential, one can then characterize or parameterize the limit surfaces in terms of this envelope construction. So namely, we have this is a more detailed description of this envelope construction, that we have some ratios of harmonic functions. And as a corollary, we obtain this something which relates to the shear phenomenon. In that case, we have a holomorphic dependence for in all these coefficients. This is some specific examples. Maybe I skip this and just let me finish that with this kind of summary, that in the free fermionic models, the important property was that it has constant Hessian determinant. In the 5-vertex case, we found that this trivial potential property is important, and then it would be very interesting to go one step further in this hierarchy and find that what is the property that the 6-vertex model satisfies. So let me, since I'm from Finland, I can actually show you how life is beyond the Arctic Circle. So this is from a skiing trip from a national park in Finland, which was indeed beyond the Arctic Circle with my boys a couple of years back. Okay, thank you very much for your attention.
Let's thank the speaker.